Have you ever wondered if there are fundamental limits to what we can simultaneously know about the tiny world of quantum particles? It turns out that sometimes, measuring one thing perfectly makes it impossible to know another related property with precision. In quantum systems, conjugate variables are pairs of physical properties that cannot be precisely known at the same time. If you measure one of these variables with high accuracy, your knowledge of its conjugate variable becomes inherently uncertain. The core reason for this lies in the very fabric of quantum mechanics, specifically the Heisenberg Uncertainty Principle. This principle states that, for certain pairs of properties, there is an intrinsic, fundamental limit to the precision with which both can be simultaneously known. This isn't due to limitations of our measuring instruments, but rather a property of nature itself. These variables are represented by mathematical entities called operators in quantum theory. When these operators do not commute, meaning their order of operation matters, they are said to be non-commuting operators. Non-commuting operators are the mathematical signature of conjugate variables. The act of precisely measuring one variable, like a particle's position, inherently disturbs its conjugate variable, such as its momentum, making its value spread out across a range of possibilities. It is like trying to measure the exact location and speed of a tiny, buzzing fly with one brief flash of light. The light that illuminates its position also gives it a kick, changing its speed. So, what does this mean for understanding quantum systems? The most famous example of a conjugate pair is a particle's position and its momentum. If you know exactly where a quantum particle is, you have no precise idea of its momentum. Conversely, if you measure its momentum with absolute certainty, its position becomes entirely uncertain, potentially spanning a vast region of space. Another key pair involves energy and time. The more precisely you try to measure the energy of a quantum system, the less precisely you can define the exact time interval over which that energy existed. For angular momentum components, knowing the value along one axis, say the z-axis, means you cannot simultaneously know its values along the x or y axes with certainty. This deep connection between conjugate variables extends beyond basic physical properties. Mathematically, these pairs are often related by a Fourier transform. Think of how a musical note can be described either by its precise duration in time or its exact frequency spectrum, but not both simultaneously with infinite precision. This mathematical relationship is formally captured by something called canonical commutation relations, which are fundamental equations that quantify the inherent uncertainty between these variable pairs. It is a cornerstone of quantum field theory and advanced quantum mechanics. Understanding conjugate variables is crucial because it reveals a profound and inescapable aspect of reality at the quantum scale. It tells us that our universe is not simply a collection of perfectly defined properties awaiting measurement. Instead, some properties are inextricably linked, and probing one necessarily influences our knowledge of the other. This insight helps us appreciate the probabilistic nature of quantum mechanics and is essential for designing and interpreting experiments in quantum computing and fundamental physics research.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.